And I really hope that this session is something that's very useful for you. I really hope it will be sort of interactive and hands-on. So my kind of rough sense, I mean, I have a confession to make. I'm not an expert on two-year colleges. I believe that most of you teach at those. I have heard a bit, sort of Tom and Chris and Joe have kind of tried to get me up to speed a bit. And so kind of my working model is you're teaching kind of students primarily, it's sort of, I'd say, non-calculus based, correct me if I'm wrong, so either algebra or conceptual. And many of these students maybe don't have a traditional kind of strong physics high school background, certainly maybe have not taken AP physics. And maybe for some of them, the two-year college is at least, I think, sort of a bridge if they want to get into some sort of four-year program or sort of just strengthen their physics skills from not having taken that much physics in high school. So again, please, oh, some of us do teach calculus based, but definitely not necessarily with any high school physics. Tiffany, I teach calculus based. Okay. Okay, Joe. So it sounds like, yeah, there's quite sort of a range. So this is good. I'm learning something already. Thank you very much. Maybe I might like just to start off, if you could just let me know, it just helps me with my mind to get a nice sense of kind of where you teach geographically, in the US, or maybe one or two are beyond that. So if you could just type in the chat, whereabouts you to teach, just the location and your institution name. And if you could just let me know one thing that you're hoping to get out. You've given up your valuable time in coming to a quantum workshop. So where you teach, what institution, and one thing you're hoping to get out. If you could just type into the chat, that would help me. Okay, Tom, near Houston, thank you very much. Pasadena City College in Pasadena, California. I do know I was at Caltech once and there was a college right next to that. I wonder if Pasadena City College is that one or if it's a different one just down the road. At UWF Texas Weatherford College. Okay, mostly calculus based. Hickory, North Carolina. Local community college. Okay, a high school teacher, Michael, quite a number of people from Texas, Maryland, near Washington, D.C. Used to live in Southern Ontario. Fantastic. Trincanon, to get a better understanding, I teach Baton Rouge Community College in Louisiana. Lisa, and the algebra-based instruction, mostly biology students. Okay, I'm glad you mentioned that. I do have to say the first time that I taught kind of biology and medical students for physics, this was at a university. It was a whole new sort of, I guess, sort of different kettle of fish to me, and I needed just to sort of adjust my teaching. So it's good that we have that group, but great that a lot of people want to learn physics. So thank you very much. I hope that sort of definitely has given me a bit of a better sense of the group. I hope, again, that this will be useful for you. Most of the stuff that we do is for high school students, Canadian high school students. But again, I hope that this will be useful. I kind of want to start off with this because I don't know about your students, but I always find it useful just to remind myself that really most students don't know a lot about quantum. So I would say quantum is definitely out there. It sort of has kind of permeated the popular culture. But certainly when I talk to Canadian high school students, I suspect the situation is the same in the US. This is kind of, if they know anything about quantum these days, the last few years, this is kind of what they know about through Hollywood, for better or worse. So I just kind of keep that in mind. And obviously, it's not a scientifically accurate documentary, but at least they know something. So for me, it's sort of a starting point. You have to start where students are at. And for me, one of the goals is really to start again where students are at and get them to kind of some genuine sort of real knowledge of quantum physics. So when I'm teaching sort of introductory quantum physics, that's really one of my goals. I'm sure I do not need to tell you this, but for me, I feel quantum is a very challenging topic to teach. It's quite abstract. A lot of teachers tell me at all levels, it's quite hard to do sort of hands-on. Many traditional, at least university courses, when I learned quantum, it was very mathematical, solve the Schrodinger equation. And for a lot of students, that really wasn't sort of a great fit. And so really we've tried to kind of think about trying to make quantum more accessible, and for a big thing, especially at the high school level, to make it more hands-on. And really with the ultimate goal of getting students engaged, not teaching them everything about quantum, but just teaching them kind of a little bit of a bit, just to get a sort of a base of kind of quantum knowledge. And so that's where we want to get to today. As Tom mentioned, this is a building where we are. This is Perimeter Institute for Theoretical Physics. It's sort of one of the largest kind of theoretical physics hubs in the world. We have a couple of hundred researchers working on everything from cosmology, the Big Bang, down to quantum physics and the smallest objects and particles that make up everything in the universe. But as well as that, we have a dedicated outreach team, and that's part of what I work on. And really our mission is just to kind of share knowledge, kind of the love of and excitement of science with the wider community around the world, including high school and college teachers and students. Yes, we are in Canada, but I always like to, when I look at a map, we're pretty close, at least to a lot of parts of the US. I think Niagara Falls, New York, is the closest city in the US that we can get to. It's probably about an hour and three-quarter drive if it's a short border crossing. We can get to Detroit and Buffalo in about 3-4 hours. And I think I drove to New York City, Manhattan, about sort of 9 hours once. So yes, we're in Canada up here, but it's really sort of fairly close, definitely, if you sort of live in sort of the east or northeast of the United States, sort of just across the border. So one of the things we do is we make educational resources. This is one of the latest ones that we have. It's called Quantum Technology. Every resource that we have is we distribute for free. And we have a resource center. If you Google Perimeter Institute Resource Center, you can get to that, and every single thing that you see there is for free. So I have free educational resources, and pretty much everything I'm going to be going through today is from this resource here, so Quantum Technology from our resource center. Even though generally when I'm teaching science, especially to high school students, I like to also teaching quantum physics to high school students, or even sort of introductory college students, I like to kind of really start not with quantum and really take a step back and look at something a bit more familiar, a bit less intimidating, because I definitely think there's an intimidation factor with teaching quantum, and just remind them of how science works. I'm sure they know this, that science, a really key part of it is making models or theories. And we do that through observation and inference, whether it's electromagnetism, Newton's laws of motion, relativity, quantum physics, whatever it is, they're all models based on observation and inference. And really, in essence, in a way, a model in science is just our best guess based on the data that we have in front of us. And that's kind of the way science works. It's empirical. And ultimately, quantum physics, as scary as it might seem, is just another in a long list of models about how the world works, particularly how the world works on the really, really smallest scale. So atomic, subatomic. So yes, it's a little weird, but ultimately it's just another of the many scientific models that students have learned. So we're going to do a few breakout rooms. I think the worst thing I could do would just be to lecture, especially, I'm sure, to a group of teachers. I'm sure you've got some amazing, good, effective pedagogical strategies. So what I have here is. So there's just a homemade setup. On the left there, there's kind of a pink ruler, which is just a ramp. And in a minute, I'm going to show you a little video. I'm going to get some marbles. And the ramp, it's pretty steep. I don't know, just eyeballing it, it's maybe about 70% incline. In a minute, I'm going to get some marbles and kind of you'll see in the video, sort of roll them down. There's a little groove there in the ruler down from left to right, and they're going to roll across to the wood there on the right. So the wood, I don't know, hopefully you can see that in the picture. It's sort of two sheets. There's a gap of, I don't know, about 2 centimeters, which I guess what that's sort of just under an inch there. The black is just some sort of plasticine, Play-Doh type stuff, just to make kind of a smooth ramp up there to the bottom of the lower sheet. So there's a little gap, and in between the gap there in the wood is something. Now you can't see it, but trust me, there's something there. So in a second, I'm going to show you, just get out of here. I'm going to share with you a link in the chat. And when you get that link in the chat, in a minute, if Tom or Joe, Tom, I think, if you could put people into breakout rooms, about 3 or 4. And I guess I'd like you to act as your students. And think like your students. And so watch the video. It's about kind of 3 minutes, and use your observation and inference skills to really try and answer this question that you can see there. What do you think is between the wooden sheets? There's something there in the gap, almost like a kind of a sandwiched in the middle, based on watching the video and watching, I think it's about 10 or so marbles rolling down the sheet. So I'll put the link up in a minute. And then I think that should still be available when you go into your breakout rooms. So if you could kind of click on that, watch that. I don't think there's any sound in it. Goes for about 3 minutes. And then again, thinking like your students, nothing fancy, just come up with a sketch, think of it in your head, kind of what do you think generally? No, again, looking for anything too sophisticated. What is between the sheets? Okay, so here, if I stop sharing, okay. Let me see. Okay, if I very smoothly do this. So, okay, so that is a link to a video, hopefully will work for everybody. So that's a video to watch. Basically marbles rolling down the ramp. Tom, when you have already put people into breakout rooms, and again, thinking like your students, come up with a picture, either a mental picture, feel free to get a scrap of paper. What do you think is in between the 2 sheets? Whenever you are ready, feel free to put people into the breakout rooms. Tom.
I am actually doing the breakout rooms, and I
Sorry.
will
Sorry,
create
Chris.
them
Okay.
now. No worries. And we'll say, what, 8 minutes?
Oh, this looks like a very intelligent group, I can tell. So I think they'll only need about 4.
Oh, okay. Excellent. Breakout
We need
rooms.
time to watch the video,
Oh, okay. Okay, sure.
and
Okay.
it's almost 4 minutes.
Okay. Okay, yep, let's go. Eight also works fine. Thank you, Lisa. Absolutely. So I think we are all back now. So I would just invite you to type into the chat if I showed this video to your students. What do you think how would they describe what is in between the 2 sheets? What kind of model would they give? Again, feel free to type that into the chat based on watching the video, what they can see, and also what they can infer being good scientist. Libby, my students would probably draw a picture of a surface that was jagged or different sides to explain the different directions, right? There's some kind of collisions and reflection going on with the marbles going off in different directions. The marbles are reflecting off some object inside the black box. The reflecting object probably needs to be circular. That's a decent guess. So we could kind of spin something repels the marbles. Awesome. Tiffany, oh, awesome. That's a little shape. It's It's sort of like a bucket or something like that. I'm assuming the bottom of it is what is facing directly into the ruler, upside down bowl. Awesome. That is a good guess. I'm going to be very mean and actually not tell you what the answer is. All these models that have been suggested are quite good. And the reason I do have a purpose for kind of being mean, and that in quantum physics, this is really for me a sort of an analogy. For the situation we face in quantum, that we, have these experiments that we do in the lab, spectra, whatever. We can make some observations, we can get some kind of output. But then, nature never tells us exactly. We can't open up, the box. Well, we can open up the box that Schrodinger's cat is in, but we can't open it up and and see what it was before we opened it up. So a lot of what we do in quantum physics and other areas is really, it's somewhat indirect. So there's a lot of inference involved. So it does make it challenging. We can't directly sort of see in a very direct way inside an atom. And so it makes it challenging, but that's kind of the situation that we have. That's the reality we have to deal with. And so for me, I often find kind of the sort of the analogy of good scientist and a good quantum physicist really being a detective, basically kind of following kind of the clues, trying to come up with the best hypothesis that you can. And I find this useful, certainly for high school students, just to kind of set up sort of where we're going. And again, just start with something that's a bit more familiar, less intimidating, hopefully kind of give them a little bit of confidence before we delve into kind of the quantum world. Tom, do you use different shaped objects inside the wooden sheets? So I just have one, but if you look online, particularly CERN's outreach team, they have a whole bunch of different shapes. I think they have almost like little mazes, but you can find them online. Other people as well, they have a whole lot of different shapes. I believe they have some with instructions for kind of 3D printing, which is really, really good. But you can find a lot of different shapes. And yeah, this is really good, maybe to kind of give students multiple shapes. So yeah, definitely you can set it up. The limit is your creativity. So if we're learning about quantum, one question we might have is, what is quantum? What does it mean for something to be quantum? And so let's start with an example I kind of hope that we sometimes use. So quantum, as I said, is sort of in the popular culture these days. And many people, many advertisers, many products, many things say that they're quantum. Quantum is a buzzword out there. And so I don't know about the US, but definitely in Canada, you can go to your local grocery store or supermarket and go in the laundry detergent section and find some quantum dishwashing powder. Now, is it really quantum that you're using to kind of clean your dishes? Well, maybe, maybe not. To really kind of, if we want to be sort of very exact and answer this question very sort of carefully and properly, I think this leads to the question is, what is quantum? So we have to know what quantum is before, that's probably, we want to get that straight before we can kind of answer the question, is X quantum or not? And so that really leads into the question, what is sort of a definition of quantum? And I will say, as probably many of you will know, language, many areas in physics, this is true. Language gets quite challenging. There's a lot of jargon involved in quantum. So over the next kind of hour or so, I hope to kind of sort of unpack some of that and sort of demystify it and help your students. One of the things that we found really useful is to sort of start. There are I would say, 4 or 5 kind of key ideas in quantum, key kind of foundational concepts: probability, superposition, quantization, etc. And so we're going to now sort of dig into some of those and sort of almost tackle quantum kind of piece by piece. So definitely quantum is probabilistic theory. Probability, randomness is definitely a key part of that. And so we found it really useful just to kind of tackle that in a very sort of accessible way, scaffolding up. And certainly we find in Canada with high school students, yes, they've learned about probability for a while. My son is in grade 6. He's learning about probability. But we also find that a lot of students don't really have a strong intuition about probability. They're kind of sort of a bit unsure about it. So we have an activity that now sort of really is sort of a gentle introduction to probability, just in general, leading into quantum. So now I'm going to give you another link. And Chris, if you could, in a minute, when I put the link in the chat, put people into breakout rooms, probably for about 10 minutes or so. What you will find is about 4 or so questions. And there's also, 3 or 4 paragraphs to read. So if you could kind of work your way through that. And whenever you're done, come back to the main group, and then we'll kind of just kind of review the answer to kind of the last question. So again, this is meant to be sort of a gentle introduction. There are some questions. It talks about tossing coins, and actually a hands-on activity where I ask you to toss a coin. If you happen to have a coin with you, great. If you don't, really any kind of two-sided object, this is just my security card here, would work. A small book, probably you don't want to toss your phone. If you can kind of improvise and actually do it, that's fine. If you actually don't have any kind of two-sided object in front of you that would substitute for a coin, then use your imagination and just sort of do a thought experiment of tossing a coin. I think it is 10 times. So I will just go on, come out of here, give you the link in the chat. So if you could follow that, there are about, again, 5 or so questions, something to read. And Chris, whenever you are ready, feel free to put people into the breakout rooms. And when you're done, come back to the main room.
All right, so breakout rooms are going to open, and I think I've only given you 15 seconds once you get the warning to come back.
Yeah, I think, everyone is back. So,
Not quite.
Oh, okay.
So maybe it was the probability of people reading directions versus not. We're
Okay.
looking at that.
Well, there were 2
Okay.
buttons there.
Okay, everyone is back now.
Great. Okay. Thank you for that. Yes, probability is everywhere. Yeah. So yeah, thank you for engaging in that. My apologies if it wasn't clear that there are multiple slides. So if you didn't do all of the slides, I mean, I think the link is still up there. Feel free now to kind of sort of glance through them, skim through them. But even if you just did the first slide, essentially that's kind of meant to be a gentle introduction, just kind of giving some students some idea, hoping to build up some kind of basic intuition about probability, and knowing the idea that yes, you can have probability that if you toss a coin, it's a 50% probability of getting heads, 50% of getting tails. But if if you do that 10 times, you have a sample, you're not guaranteed to get 5 heads and 5 tails. So you do get some kind of sample sort of statistical fluctuations, and that's probability. That's kind of the unpredictability of probability. But the main point we're trying to get really with this question, this is really a bar chart with probability and data from the Large Hadron Collider that actually led to Nobel Prize winning work discovering the Higgs boson. And we did have one discussion in one of the groups that maybe this would be a bit of a big leap for students. and which is fine. So everything that we do is sort of is editable. We know that everything we have teachers will change and modify. So we, encourage you to kind of change. All the student activities we have are in Word files, so it's easy for you to change. So if you want to sort of adapt this, something would work better for your students, we absolutely encourage this. This is, we're not selling anything. This is all sort of free resources. So yeah, thank you for pointing that out. The main point we're trying to get here is just you can think of this as a bar chart. And if you look at really just the red and the blue areas, first of all, they got quite high. We're talking about quite a lot of events, up to sort of 100 and almost 140 there. And there's both sort of large areas under the blue and red parts, but just that, so we have a fairly large sample size. And so that allows the scientists at the LHC to make fairly good, solid predictions, even though the probability of observing any one particle at one energy is quite unpredictable, it's quite random. It's very hard to make reliable inferences when we have a large sample size. Even if we've got a quite random, quite stochastic process, we can make fairly reliable kind of predictions. We can do good science. And that is typically, that's I would say, a hallmark of quantum, many other areas of science as well. You get probability in classical physics, but probability is inherent in quantum. And so one of the reasons we have this is, at least in Canada with high school students, they sometimes have this idea, oh, quantum is random. So that means we can't know anything. It's just absolutely random. The world is anarchy. Scientists cannot make any predictions. Science just collapses. And so we're really trying to get across the idea that no, in spite of this, if you have large sample sizes, you still can make some predictions. Not perfect, not exact, they're probabilistic, but you can still make some sense of the world. And that was really kind of the main point we're trying to get across there. So I hope this was kind of useful. I'll just sort of pause now. And so we're kind of about sort of halfway through. I have not got as far as I would along. I'm just going to go now to kind of the next point. We've got kind of one, quantum phenomena. And the other key idea that we find is sort of superposition. And that's really a kind of a key point. It's very sort of throughout all of quantum physics. And again, it's one of those things where superposition is a key idea in quantum, but it's not exclusive to quantum. As you know, any classical waves exhibit superposition. You can get a superposition of two sound waves, two water waves, whatever. And so it's kind of a weird quantum thing, but also at its core, it's something that is at many is in nature at kind of many levels. I always like to emphasize that quantum, in many ways, in my opinion, is sort of an evolution in our understanding of knowledge about the world rather than a revolution. And so I think that helps students build up their kind of confidence that they don't, when they get to their quantum class, need to throw everything they've learned in physics before out and start from scratch. I think that would be quite sort of scary if you sort of completely pulled the rug from underneath them. So I like to kind of emphasize sort of the evolutionary nature of quantum. Oh, is there a new slide we should be seeing? So Libby, you should be seeing kind of phenomena to superposition. There's a link to, let's link this to a common radioactive occurrence.
You're still showing, Damien, probability prompt 4.
Oh, okay.
We're not back at your slides.
Okay. Is it changing now?
No.
Okay. So I'll just do some troubleshooting on the slide. There must be some strange quantum fluctuations going on. Okay. let me go. So does everyone see a slide now as kind of the big yellow and black radioactive kind of
Yeah.
warning thing?
Yes.
Okay,
Yes.
awesome. Okay, oh, wait. Okay, do you see that?
Yes.
Still now? Awesome. Yeah, I kind of explained that. Okay. Okay. Thank you for that. Not quite sure what happened. I think what happened, I was sharing the wrong screen. So my apologies for that. Okay. So superposition, we've got another little activity here for you just to work through superposition. This is something where normally we do this in person. Again, this is just another sort of little, I would say, a mini activity where we give it, again, I'm going to put you into a Padlet again in a minute, give you a link, do the same thing. This Padlet has multiple pages. So if you could click, I think on the left, you should see multiple pages. If you kind of click through that, I think it's about 3 or so from memory. If you work your way through that, get to the final question, answer that. We find it takes people about 10-15 minutes. And when you're done, come back to the main room and you will understand everything about superposition. So stop.
Perfect.
Oh, that's good.
Wish
Okay.
it were that easy.
Ugh.
And the rooms
Yeah.
are already open, so you should be able to hop back in your rooms.
Okay,
Where's
so
the link to the Padlet?
link. Yes, the link is coming. The link just coming into the chat. Okay, so okay, thank you for kind of coming back. We had a few discussions.
They're not all back yet.
Okay, we're not all back.
Okay, now we are.
Okay, now we're back. Okay, thank you very much for that. Thank you for fully engaging in that. I hope you found that kind of useful. The main point we're trying to get out of that is really in the first sentence here. This is a copy of the text on the last slide, that quantum superposition is extremely delicate. And so quantum systems, quantum objects, whether they're a quantum computer, or any other kind of quantum system in an individual atom, one molecule. They're very, very fragile. So what that means is typically if you're an experimenter, you're measuring something, a quantum computer, any kind of quantum object, proton, radioactive atom, just the very act of measuring it disturbs it, disrupts it in some very significant way, and kind of sort of partially messes up, if you like, kind of the system, alters it. And that just makes it really, really hard to really learn anything about quantum. And so what do designers of quantum computers do? They do two things. One thing is to kind of not measure, not observe their computer, if they can avoid it, so minimize the observations. At some point, you do need to kind of look at your computer to do the readout to see what the final result is. It'd be pretty useless if you had this computer, but you never actually read out what the final output of it was. You wouldn't know anything. And the other point is really connects back to the probability point, is if you did that once, you might get an unpredictable result. Again, just like sort of tossing a kind of coin one time. But if you do it 100 times, you'll get a much more reliable result. And from that, you can actually make I guess you can learn something. You're going to get a reliable, useful output readout from your computer. And so these are the two main ways that really designers of quantum computers try to really, really combat and really sort of deal with the reality of the delicate nature of superposition. I've kind of done a few. This is sort of two activities. These are sort of mini activities, typically go about 15, 20 minutes with students. And everything we're doing is from kind of quantum or not activity one from Primitive's resource. You can see there. There's at least 3 other stations. I think there's 4 more that you can go through. Hopefully, this has given you a flavor of it. I think I have about 20 more minutes. I just love to kind of sort of just gauge the audience, the content you've had so far. Maybe if you could just give me a sense, I just want to get a sense of the level. Let me see let me see, I can see kind of everyone now. How can I zoom out, see everyone? Okay. If this would be sort of easy for your students, maybe kind of give me a thumbs up. If it'd kind of be, well, not easy, but they would get through it, give me a thumbs down, and maybe a thumbs to the side. If this stuff would be kind of challenging for your students, maybe do a kind of a thumbs down. So I'm just trying to get a sense whether I should speed up or I'm at the right speed. So if you just give me a thumbs up for this, yeah, my students would just breeze through this. Kind of, yeah, they'd get through it, or like, wow, they'd really struggle. So if I could just get a kind of a pulse of the room.
Oh,
Okay, so I think so I'm seeing there 3 to the side and 1 up. So okay, so not okay, thank you. That's very helpful. Kind of not totally off base. That's very useful. My worried, I think I was telling Chris there, I was worried that this would be kind of too simple. So we will just sort of dive on in. Okay. Oh, thumbs to the side. Okay, so let me speaker. Okay. Okay, let me try and get my PowerPoint back. Okay, oh, okay. So we're here. Okay, Michael, so thumbs up. So a few people, it's easy. So I think I'm counting 4 thumbs to the side, 2 thumbs up. So it's sort of, okay, easy side. Okay, what I might do is just for the last 15 minutes or so, just go a little bit quicker, then hopefully give something that's maybe a bit more challenging. Okay. Can you see my screen now? Phenomena 3 wave particle duality. Does everyone
Yes.
see that? Awesome. Great. Okay. So this is something, this is something that's taught a lot. Maybe you teach it. In many ways, it's sort of more quantum than superposition or probability. Really, we really don't get wave particle duality in classical physics, and really gets to the heart of quantum physics. And so we're in activity, and so really the core of it, I'll kind of speed through this just, in the interest of time. Let me see. So the core is the idea is sort of the double slit or 2-slit experiment that is taught a lot. There's a classic book, I think Richard Feynman in the Feynman lectures back in the 60s, I believe, sort of really popularized this. Although the double slit experiment, as you know, goes all the way back, at least to Thomas Young in the early 1800s. And so what we found is, again, Spirit, at least for high school students in Canada, we found it really useful to try and keep things hands-on and kind of keep things simple to really scaffold into that. So again, just sort of setting up how the classical world works, how the familiar Newtonian world works, which, students have been studying for many years and been experiencing that in their daily life for 20 years or so. And so this is a version of the double slit experiment. Students can do it at home. It's very simple. You just get any cup. If you can see there in the middle, we've just kind of sort of cut two small slits. They're a bit hard to see. They're just a few millimeters wide there. And then on the right, we've just got some sand, or I think this is salt actually. We're just going to kind of pour into that. We're going to put the cup just a little, actually there's a lip in that. So the slits are actually just a little bit above that piece of paper there. So what has happened is the salt is going to go through the slits and it's going to basically kind of end up in some kind of pattern or arrangement. And so with more time, what we typically would do is just to have students kind of predict and explain. Let's do a predict, observe, explain for what they would predict what pattern that the salt would make once it landed on the piece of paper after it had gone through the slits. I'll just fast forward. This one is not terribly surprising. That's a close-up of one of the slits. Actually doing the experiment here, then you tap. That is just useful to make the salt go through. And then kind of the big reveal, what most students predict. I find 90% of them predict this. After, you can see there's kind of two little sort of small hills or humps there. We can kind of zoom in, which I think is intuitive. One is roughly below each of the slits. Oh, okay. Yeah, Joe, okay, that's fine. I've never seen it done like this before. Okay, no, thank you for that. I find physics is just so big. I've been to many AAPT, PTRA meetings, and people have been doing things that they obviously have been very familiar with, and that I've been new to me. So I'm glad this was new to you. And so yeah, this is the double slit experiment. You can see there's sort of two piles or two humps. But really the punchline here is this is how classical Newtonian particles behave in the Newtonian world. Again, not surprising, but again, we're sort of building up how things work in the world. And we could, if we want to, sort of get students to say, well, what are kind of the key properties that lead to this? And they are little particles. Classical particles are localized, they collide with each other, and they definitely do not interfere with each other. And again, you would sort of take more time. Ideally, you'd just kind of pull this out from students. So we can do another version of the double slit experiment, but with classical waves. If you had a ripple tank, you could do a version. If you had two speakers and a microphone, maybe you do a version. You do that version where you move the microphone along, just kind of the I guess sort of a line that's perpendicular to kind of the speakers. So you hear those sort of loud, quiet spots. This is another version where literally you just get two sort of rectangles of a transparency, any kind of clear plastic. You tape parts of a straw to one end of it, as you can see there. And then we get sort of two push pins and just kind of push them into, this is a sheet of cardboard. Hopefully that makes sense. And so this is the little white kind of straws at the left end there. They just represent the two slits. These are two plane waves that you've got coming out. And here is your screen, your detection wall, if you like. And what we're going to do is you just kind of pinch the other end of those, slide them along. And again, with students, what we typically do, oh, thank you, Chris. Yes. Everything we do, certainly for Canadian high school teachers, and what I hear from US high school teachers too, is that they do not have big budgets. And so we kind of call it kitchen physics. So everything we do, we try to make it cheap and simple as well, because teachers, at least high school teachers, don't have a lot of money, don't have a lot of time. I don't have either of those things. So we do kind of a predict, observe, explain type of thing. where you could get students to predict what will happen. And then here, this is where you really want to look at this as sort of a side-on view. You hopefully can see there's two overlapping kind of sine wave patterns. I've just hand drawn them, so they're not perfect sine waves. And what I'm doing is I'm pinching on the right there. I'm going to could gradually move. The black kind of marker is my sort of detection screen. I'm gradually going to move, slide these lines sort of along. And so what happens is basically the waves have to travel different distances to kind of get to those. And again, trust me, this works a lot better if you're in person in the room. I will do my best. There's a little video here. If you look, hopefully you can see the waves are completely out of phase. So you get destructive interference. They're back in phase, constructive interference. If I keep on going, they're getting out of phase. So out of phase, destructive interference, almost perfect there. And typically what we do with students is that they do that, but they just actually get a pencil or some kind of marker. And whenever they get to a point where you get an interference maxima, you get constructive interference, they just do a little mark on their cardboard or sheet of paper. And so what they end up with is kind of something like this, which is your sort of you could, Lisa, you could print the sine wave pattern onto transparency films. It would be smaller, but might work. Yeah, absolutely. Yeah, there are a lot of different ways of doing that. You could do that. So thank you. That's a great idea. Oh, two-year college faculty also don't have dollars or time. Also, kitchen physics helps to demystify physics. Yes, it's not. Okay, thank you. That's a good point. And so here, what you do have is you kind of just can build up something that resembles your classic textbook two-slit interference. We do know, certainly when I show this to Canadian teachers, that the bulk of what they teach is not quantum. It's Newtonian, it's waves, it's energy. And so a number of teachers, certainly Canadian teachers, say, oh, I would just use this when I'm talking about wave interference, forget quantum. Oh, multicolored roller skate laces. Okay, I could see that. That's cool. I've not heard of that one, but I think I can imagine how that would work. Thank you for that. Yeah, there are a lot of different ways, but the essence here is, and really the punchline here we're trying to get students is to realize is that the key properties of classical waves is that they're sort of spread out, non-localized. Can we get a PDF of the sine waves we could print on transparency film? Yes, Dan, absolutely. I'll put a link in a minute where you can do that, but absolutely. We have that again in our resource center. That's a resource, the challenge of quantum reality, but I'll put that in actually. Yes, I will put that in a minute. I will not forget. And so kind of the punchline here is that waves, classical waves are spread out. They interfere constructively and destructively, and that they don't collide with other waves. Two waves just pass through each other. So again, we're sort of building up this difference or distinction, if you like, between classical waves and classical particles. And so certainly in the classical world, we've got these two buckets is where we end up with. And typically, we go with students through this for in about an hour. And we've got these, these two sort of buckets of models, if you like. We always like to use the modeling language. And where waves and particles are very different. They have very different properties. If you think of them as sort of animals, they're two very, very different animals with different characteristics. And so, well, okay, what happens with electrons? What happens when electrons go through the slits? So again, essentially, we're going to do the double slit experiment. Again, just like we've done it before, but we're going to instead take out our classical waves and put in kind of electrons. And so here is, we're calling it an electron gun. And so what was an electronic gun? Essentially, it's a piece of metal. It's just a metal wire that you just heat up a couple of 1,000 degrees, and literally you boil off electrons. You excite electrons enough that they get enough energy to kind of break free from that wire. And they go out, as you can see there, from those dashed line arrows in a whole bunch of different directions. Some of them hit the side of the wall here. This is almost like an overhead view of the double slit experiment. Those sort of white little gaps are the two slits. On the right there, we've got a detection wall. And so many of the electrons just sort of bounce off the detection wall, but some actually end up, if they go through in the right direction, end up passing through the slits somehow and making some kind of a pattern. And so what we might do is we might do one last quick breakout room. Is that is all right? There are no links involved in this. So my question would be, if I gave this to your students after they'd done the setup, they'd seen the classical wave particle or classical wave pattern, they'd seen the classical particle pattern. I told them what pattern electrons would make in the double slit experiment after we fire, let's say, 1,000 electrons at the double slits. What pattern would they make on the final detection wall there? You can see there on the right. So I'd like to ask you two questions, really. What pattern would they predict? What general shape? And why would they predict that? What would their reasoning be? And just in the interest of time, Chris, maybe if you could kind of give people just kind of 2-3 minutes to go through that, if that's okay. So what pattern would electrons make if we did the electron double slit experiment with many electrons? And why? What would your students say? So whenever you're ready, put people into...
The rooms are open.
Everyone is back now. Just in the interest of time, normally what I would do is kind of ask you what your students would predict. I'm pretty confident I've done this a few times, and what we find is probably 95% of the time, the students just say, you or teachers tell me their students would say that you would get the pattern pretty much like the classical particles, two piles. Because as we all know, electrons are tiny particles. So these little tiny sort of balls or marbles, if you like. And what I hear is many students kind of have that intuition. I'm pretty sure I could find many textbooks, many online pictures of electrons as little tiny sort of spheres or circles, maybe with a negative sign, a horizontal line in them. And that's kind of the model, it's at least certainly with high school students, that they have. But again, this is science. We want to do experiments and we want to test our models. And we're very fortunate enough, this was way back. Gosh, this would have been about 2010. We actually searched around for people that actually did the electron double slit experiment. It's not a very easy experiment to do. Unfortunately, it's not something that really any high school person could do in their lab. There's sort of half a dozen around the world. And it turns out that in the US, University of Lincoln, Nebraska, actually had an probably still does, I think. I'm not 100% sure of that. There was Professor Herman Batalon there graciously allowed us to come into his lab and film that. And we'll just show you a little kind of clip. This is on YouTube. It's also in Perimeter's resource. But let's do the experiment and let's see what... So I don't know if you can hear the volume. If not, oh,
No, you can switch that when you share your screen. So go back into
yes.
share screen
Okay.
and turn on volume.
Okay. Okay. Yes. I might just narrate it through. So here we're just introducing, that's the actual slits you can see there. Well, you can't actually see it. They're so small. They're about 100 nanometers apart. This is looking at them under an electron microscope. This is the actual double slit experiment. That's where the slit is kind of mounted. It's all inside a vacuum tube here. You want to kind of remove any air out because that would sort of deflect the particles. So it's a very, very complicated experiment. I mean, it took them sort of months to set up. It's very, very precise. You have to direct the electrons in a very precise direction. This is kind of, that was sort of the results of what you would see on the screen. Again, this is on YouTube. This is real live data that you're actually seeing the results for. This is the detection screen. It's sort of flickering there. There's just electrons hitting in different regions. And if we sort of take a sort of still of that, and again, this is on YouTube, and I'll put the link where you can find that, you end up with something like this, which definitely does not well, it definitely maybe does not look like the two kind of pile pattern. So we're hoping that students would this would sort of make them second guess their prediction that they had. It also doesn't look like sort of a textbook interference pattern. This is a real experiment with noise, but I think if we look, many other groups have done it. And here are 3 different results from the electron double slit experiment. You can see there here. And I think here, to most students, hopefully these would look like interference patterns. And so this kind of result of electrons making interference pattern is a pretty solid, sort of stable result that we have a high degree of confidence in. So sort of what are electrons? Well, this sort of suggests certainly they're not sort of little tiny marbles. I'll just sort of cut to the punchline here. And again, we walk through this in more time. That one thing that we found out is that, yes, the interesting thing there, actually, I should go back, is when we actually look here, each of these little sort of dots is where one electron hit. And so if we sort of zoom in and look at any individual electron, each of them does hit like a particle. But when we kind of zoom out, these patterns here, these are the result of thousands of electrons hitting a detection screen. When we zoom out, the overall pattern is a wavy interference pattern. And so what we find is electrons almost they're kind of indecisive. They can't make up their mind. So when we look at each individual detection, the particle model is a great, perfect model for explaining it. When we kind of zoom out, look at the overall pattern, particle model, not so great, but the wave model works. And so we have this weird kind of indecisive mixture, this kind of blend. And the name that we call that in quantum physics is a wave-particle duality. So it's electrons, they have this kind of split personality, if you like. And so sometimes they behave like particles is the language that we use, and sometimes they behave like waves. What are they really? I don't know. We have researchers working on that at Perimeter Institute, many other people around the world. There's no consensus. I don't know. If you do know, you'd win the Nobel Prize in physics. So please let me know in the chat. So it's a very deep thing, but we do find as all quantum objects have this behavior. It's kind of strange, but it's not as if electrons and other quantum objects are a blend of 2 completely different models that students have never come across before in classical physics. I always like to emphasize, again, the evolutionary nature of quantum, and that these 2 familiar models, each of them are almost like 2 pieces of a jigsaw puzzle. That part of the quantum puzzle, yes, you can use the classical particle model that you've learned about, used about Newtonian mechanics for many years. And another piece of the quantum jigsaw puzzle, yes, you can happily use the wave model that you've learned about, but you've kind of got to be careful when you use them, and somehow they're sort of stitched together in a way that we don't fully understand. So yes, if you're just interested in sort of predicting the results of experiments, you can happily do that very precisely in quantum. I think many people, want to know, what is an electron really? Talk to 10 physicists. They'll give you 10 different answers. There's no consensus model on what a picture of an electron is like. or any other quantum object. That's maybe not something a student wants to hear when they're learning a subject that even the experts don't know. Maybe you would phrase that differently for some students, but that is the reality. And to a scientist, that's very exciting. And that's true. There's a lot we still have not figured out about quantum, and that's just the truth. We're working on it. But hopefully some students may be excited by that. Maybe some will be scared. I don't know. This kind of brings to the end of my time. I just want to end by thank you very much. I'll stay on afterwards if anyone has any questions. But everything I've done pretty much is from activity 1 from the quantum technology resource. The sine waves, and I put the link in the chat to that before, I'll put it in again. The sine waves and the wave transparencies that we saw, so this kind of stuff here, this is from the challenge. So this is from the challenge of quantum reality. I put a link in the chat. Again, you can download both of these completely for free. I'll put some more links up again to show you exactly where. Thank you so much for your time. I hope this has been useful. Please let me know if it was. Please let me know if it wasn't. Always love to hear any sort of feedback. Again, I'll stay on the line, and I would just love to just if you could fill out. I know Tom has and Chris have a survey, and Joe, but I would love this. Just helps with our funding and keeps the Canadian government happy. There's a QR code. If you could. Kind of just point your phones at that. That should only take about a minute and fill in that. That would be very helpful. I'll keep that up for a minute just so people can get that. I'll try and actually get the URL as well. And in a minute, I'll just take that down. I'll stop talking now. And so then I'll just let Tom do whatever he needs to now. So